Hello, and welcome to the second complex analysis class. So, we learned what the interior of a set was, right? So, int omega is the set of interior points. Which is the set of all points such that we can fit some small ball around that point and still be inside this set. Yeah? Okay. Now, let's talk about the limit points. So we say Z is a limit point of omega if and only if there exists some Zn belonging to omega such that the limit, which goes to infinity, Zn equals Z, right? And we let omega bar be a set of limit points. Okay. So we redefine this closed ball by this. So we define this thing. Okay. But this is consistent with this notation because that is just the set of all limit points of the actual ball, right? So it's consistent. Okay. And we say omega is closed if it's equal to its set of all limit points. So okay, good. So an example, if we let omega be the set of all x plus iy such that, say, 3x plus y is bigger than or equal to, let's just do bigger than 0. Okay, so let's visualize this. This condition that 3x plus y is bigger than 0 is equivalent to 3,1 dot product xy is bigger than 0. So if we draw the vector 3,1, it looks like this. The dot product is bigger than 0. Let's take the perpendicular line to this, like this, yeah? And what is the set of points? This is strictly positive. It's everything in this half plane like this, right? And this is an open set because if we take any point for which this is true, we can for sure put a little ball around it and still be inside this, still satisfy this, right? Because it's a strict inequality. Yeah. So this is an open set. It's equal to its interior. Yeah. What's the set of limit points of this thing? It's everything inside this set, of course, plus this line defined by this. So omega closure is equal to omega union this line, the set of x plus iy, such that x, y dot product 3,1 is equal to 0, which is exactly this line perpendicular to this vector 3,1. Yeah? Because those are the only additional points we get from adding the limit points. Yeah? And if instead of defining it this way, if we define it with this strict equality replaced by greater than or equal to, then we would have a closed set, right? Because then, as we just discussed, the limit points are just the set itself plus the line, and that's exactly the same thing as what we'd get if we had this thing replaced by this. Yeah? So these things are probably all familiar to you. So that's open. That's what we mean by a closed set. And a compact set is a closed and bounded set. So we say something is bounded. Back to this color. We say omega is bounded if and only if there exists some m such that what z is less than or equal to m for all z belonging to omega. And this is equivalent to having that omega is contained within the closed ball of radius m around 0. Okay? So, something is compact if and only if it is closed and bounded so for example, the closed ball is compact, it's closed and bounded. What other notions do we need? We need connectedness. So we're going to find connectedness just for open sets. So given open set omega, we say omega is connected if and only if whenever we write omega equals omega 1 union omega 2, where omega 1, omega 2 are disjoint open sets, if and only if then one of them is empty, then either omega 1 equals the empty set or omega 2 is equal to the empty set. In other words, we can't write this as the union of two disjoint open sets. Okay, so it comes with the picture, of course. So if this is omega, then it's not connected because it's the union of two disjoint open sets, right? So, not connected. And for open sets in the plane, this is, well, for open sets in Rn, actually, this is equivalent to being path connected, which means that omega is path connected if and only if there exists a path, which is the image of a one-dimensional line segment into our set that goes through any 2 points, Z1 and Z2. That connects any 2 points. Okay, so these are these basic topological notions we need to be happy with. They are, I think, familiar to most people. You've seen them before, and that's about all the topology we'll need. So let's erase the board and start to talk about some theorems. It's not quite all the topological notions we'll need, because we also need the notion of a boundary. So given omega, the boundary written like this, is set of limit points take away the interior points. Okay, so the boundary of a ball, for example, the set of limit points is the closed ball, the interior is the ball itself, so that is just going to be the set of all z, such that mod z minus x is actually equal to r, right? As you can see pretty easily, right? So this thing is the circle around the outside. Sometimes this is written as C for circle. I don't want to C of R of X, C of R. Sometimes it's written like this. I don't want to do this notation because it's not worth it. It's just easier to write the boundary of the ball, but that's what you sometimes see for the circle. Okay, good. So that is the boundary. This previous example we discussed, omega is the set of all x plus iy such that 3x plus y is bigger than or equal to 0. The boundary is exactly this set. I think I even said that, where 3x plus y is equal to 0, which is just a straight line perpendicular to the vector 3, 1. Yeah? Okay, let's talk about continuity. We say f from omega into the complex numbers is continuous at, say, z0 if and only if for every epsilon bigger than 0 there exists some delta bigger than 0 such that f of z minus f of z0 is less than epsilon for all z minus z0 less than delta. Obviously delta depends on epsilon. And this is the picture. So we're going to have to visualize complex functions, or complex valued functions from the complex numbers as deformations of a two-dimensional space into a two-dimensional space. So this, say, is omega, right? This is our point z0. This function maps this thing into a subset of the complex plane, so it's a two-dimensional blob in the complex plane. So I'm going to draw something like this. Maybe it looks like this, who knows, right? And right here is some point f of z0. Yeah? So what does this condition say? It says that if we put any ball of size epsilon around this point, like this, so this is our ball of size epsilon, this is epsilon here, then we can guarantee that the ball of size delta is mapped into this ball so long as we choose our delta small enough, right? So in pictures, that is saying that we can put some little delta ball around z0, so this here is delta, okay, such that the image of this little ball is contained inside this ball. So this is the image, right? This thing right here is f of the delta ball around z0. So for any epsilon ball around f of z0, map this guy inside this guy, right? So this thing is the concept, and this thing is expressing the concept in the language of math. This is the real thing here. Okay, cool. That's continuity, and we say f is continuous on omega if and only if f is continuous at every point on omega. Okay, cool. All right, so that's continuity. This stuff is the same as you would do in any metric space. This doesn't use any properties of the complex numbers that are specific to the complex numbers yet. Let's just state a theorem about continuous functions. So if omega is compact and f is continuous on omega, then we have, let's actually call this theorem 1. That there exists some zeta belong to omega such that the absolute value of f of zeta is equal to the supremum of f of z for any z belonging to omega. In other words, we can achieve this value. So let's draw a picture. So this, say, is omega, it's compact, and it's mapped to something like this, say, right? Wherever, let's say 0 is here, and this is f of omega, okay? So what is this number? Let's actually just call it m. This thing is this, right? This thing is this. This is how far away from 0 we can get with elements of f of omega, right? So this thing here is m, right? It's the smallest value for which we can contain this thing inside a ball of radius m around 0. So I can't draw an entire ball, but you see what I'm doing. Yeah? And the claim is that we actually have some zeta, wherever it is, it's actually going to be here, which achieves this guy. Okay? And this follows from continuity and the fact that every compact set has a sequence. Every compact set with a sequence inside it has a subsequence that converges to a point inside that set. Yeah? And both of these things are elementary things that you can easily prove with a little bit of thought. Okay, maybe I give you a hint. Of this. So if you did real analysis, you probably saw something called Bolzano-Weierstrass, which on the real line is saying that if you have a sequence that is bounded on the real line, there has to be a subsequence that converges to a point. And you would argue like this. You'd say, okay, if it's bounded on the real line, it's between some a and b. Right? So we have this infinite collection. Let's not put them here. We have this infinite sequence of numbers between a and b, all these guys, right? So if there are infinitely many of them, then if we cut our interval into 2 pieces across here, so this piece, say I2, and this piece I1, then one of these has to have infinitely many members of our sequence. Let's call our sequence xn. So this is x1, it doesn't have to be, let's say this is x3, this is x1, whatever, and whatever, xk. These are all elements of our sequence. And one of these I1 and I2 has to have infinitely many of them, right? Because they're all inside AB, which is the union of I1 and I2. Yeah? Cool. So if it's I2, which has infinitely many of them, I mean, both could have infinitely many, but at least one does, then we can split I2, again, into 2 things, right? We'd split it across here. And let's call the next generation J1 and J2. Yeah? And again, one of these guys, J1 or J2, has to have infinitely many members of our sequence, right? So if it was J1, then we are here. And then we split J1 as well, right? We keep splitting and splitting and splitting. And every time we have a smaller interval that has infinitely many members of our sequence inside. So we can just pick some guy from here, and then some guy from here, and then some guy from here. And at each stage, we pick some guy inside a new generation of cutting the interval in half. And then that subsequence must exist because we keep being able to pick such points. and it must converge to some limit because we keep getting smaller and smaller and smaller. Yeah? That is so-called Bolzano-Weierstrass theorem, argument, whatever. And indeed, it will work if you do this in a metric space. If you do this in the complex plane, then you might break things up, for example, into squares, right? And then just argue in exactly the same way. So if you have a compact set inside the complex numbers with a sequence inside it, there must exist a subsequence that converges to a point. Yeah? So what we would do is we would find some subsequence. So we'll find some sequence, I should say. So let zk be such that the absolute value of f of zk is bigger than m minus 2 to the minus k. For sure, we can find such zk because that's the definition of m. Yeah? If we couldn't find such a zk, then m would have to be smaller than it is. Yeah? And then take a subsequence that converges, because this is inside a complex set, it has a subsequence that converges. So take convergent subsequence which will converge to some z, which will belong to omega. Yeah? And then what? Well, if we visualize this, let's put it somewhere. I'll put it over here. So we have our guys here, right? So this thing is m, and they keep getting closer and closer to the outside of this ball of radius m, right? So if this thing here is m minus 2 kn, then we have some zk outside here, right? That's the definition. Yeah. So this guy would be our zkn. Yeah. And this sequence of points is converging somewhere, and it has to actually be here on the boundary of the ball of radius m around 0. Because there's nowhere else. It's being forced outwards, right? And it's converging to some point. Or you could say this thing, z goes to f of z. This is the composition of two continuous functions, because the absolute value is continuous, as the triangle inequality says, right? So this itself is a continuous function, and therefore, if we apply the fact that this is continuous to our sequence, we have that the limit as k goes to infinity, n goes to infinity, of absolute value f of zkn will have to equal to m. It can't be bigger than m, and it has to be bigger than any number less than m, so it's equal to m. Yeah? By continuity, so this is not so, this is just an definition, so, and so by this fact here, we have that the absolute value f of zeta, which is the limit of this subsequence, is equal to m. So I didn't actually say that anywhere. Taking convergence, yeah, I call it z, but I want to call it zeta, is equal to m. So by continuity of this thing, this has to be true, because this is true, right? So I prefer to think about it this way, right? I prefer to draw the pictures rather than use principles, but it should be kind of straightforward. Yeah? This is a straightforward theorem. All right, cool. So I'm going to raise the board, and now we're going to start the subject properly. We're going to start to talk about differentiability, which is where this thing really gets going. Okay. Okay, so we're going to consider some function f from omega contained within the complex numbers into the complex numbers, which is differentiable Well, let's do this as definite. So this is differentiable at zeta if and only if the following is true. And what I'm about to write is exactly the definition of differentiability you've seen many times before, but now we're writing this in the complex field, and it means something very different. So we have the limit as h. I'm going to emphasize that h is a complex number, right, like this, goes to 0 of f of zeta plus h minus f of zeta over h. So this quotient, you know from calculus, you've seen it many times before, you know what it means. This is the completely familiar expression. This looks exactly like the definition of differentiability from the real numbers to the real numbers. Huh? But this is a very different thing, because now we're using the field properties of the complex numbers in writing this, because this thing at the top is a complex number, this is a complex number, we're dividing complex numbers, we're using the field structure of the complex numbers, what it means to multiply or divide complex numbers when writing this. And that changes the entire thing. That makes the entire thing totally different. This is where the subject of calculus of complex valued functions and calculus of real valued functions go on completely different paths. Because simply doing this is the natural definition of differentiability, this is the correct notion. Simply doing this and asking that it exists starts us off on a totally different path, because this means something completely different. And this is what I'm about to explain. Okay, so we say it's differentiable at zeta if and only if this holds true. Okay, and this is the natural and the useful notion, right? This is indeed a complex number because it's the limit of these two things, and they're both complex numbers. And yeah, this should be believable as the natural notion of differentiability. What is the point of differentiability? Differentiability allows us to take something which might be complicated, like a function, look at it on a very small scale where it is simpler. Where we can analyze it, because on a very small scale it looks like an affine function, right? A linear function plus a constant, right? Which is what this thing is ultimately saying. This is saying that let's just write it. So this is equivalent to saying that f of zeta plus h is really a lot like this thing. It's like this complex number times this complex number plus this fixed complex number, because we're moving h, right? Plus some small error. Well, if we put the small error, then it's actually equal. Let's use this notation, where this thing goes down to 0 faster than the absolute value of h, right? So I don't need to put modulus inside, I guess I just put h. So this is the error here, and this thing is going down to 0. This. Let's write it like this. So on a very small scale, around the point zeta, we are a lot like just an affine function. This is a complex linear function plus some kind of a constant. Yeah? Cool. So let us develop the consequences of this. So some notation. So we write f of x plus iy as u of xy plus iv of xy. So u and v are just mappings, therefore, from R2 into R. Right? So this is a very common notation. It's very convenient to write them like this. Yeah? And let's see the implications of the definition of differentiability. So let's take complex plane. Here is 0. Oops, but make it bigger 0. And let's take the limit as h goes to 0 of this quotient. But now, remember, we can do this as h goes to 0 in any way, right? Because all the requirement is that h goes to 0. So we go to 0 along here, along the real axis like this, yeah? So let's start by doing that. So if we look at this thing, then what are we going to do? Let's take the point z to be consistent with this notation. So if f is differentiable at z equals x plus iy, then the following is true, that if we take the limit as alpha goes to 0, let me emphasize that alpha is real, just a real number. Alpha belonging to the real numbers goes to 0 of f of z plus alpha minus f of z over alpha. This thing has to equal to f prime of z. That's the definition. Alpha being real is still a complex number, right? Because the real numbers contain the complex numbers. So this thing implies this thing, right? And let's write out what that means in terms of u and v. So let's call this thing star. So star is equivalent to the limit as alpha goes to 0 of u of x plus alpha y plus iv of x plus alpha y minus u of xy plus iv of xy over alpha. This limit has to exist, right? We can break it up into the real and imaginary parts together. So that's equal to the limit as alpha goes to 0 of this u of x plus alpha y minus u of x y over alpha plus iv of xy or x plus alpha y minus v of xy over alpha. Yeah, just doing some algebra here. Okay, let's look at this. So this thing is meant to exist. It's meant to be equal to f prime of z. And I claim that implies that both this limit exists as alpha goes to 0 and this limit exists as alpha goes to 0. Yeah? So from real analysis, you know that you can't necessarily conclude that, right? Because it could be that if we were just having these two limits and there are real valued limits and we added them together, the limit could still exist, even though the individual limits of the sum of the two don't exist. They just happen that when we add them together, whatever oscillations is canceling itself out. Yeah? That can't happen here because this guy here is on the real numbers and this guy here is on the imaginary numbers, right? So if this thing as alpha goes to 0 doesn't have a limit, there's no way that this guy can save it so that the sum of these two guys end up having a limit together, right? Yeah? Another way to think about this is just to say, okay, we could take this complex number and project it down onto the real numbers, right? And if we did that, then we would not see this guy, and we'd just see here the real part of this, and therefore we would have that this limit would have to equal the real part of this, right? So this thing has to have a limit by itself as alpha goes to 0, and so does this guy for the same reason. Yeah? I don't want to write out this because it's going to take too long, but hopefully it's going to seem natural to you. If you're in any doubt, write out what I just said in the language of maths. Yeah? Literally write what I just said. Project this thing onto the real numbers, write out what that means, right? And then project in the complex numbers, and you'll see that this has to be true. Yeah? Okay, so both of these limits exist, so we can write this entire limit of the sum is the sum of the limits, and the limit of this thing as alpha goes to 0 will just be the partial derivative of u with respect to x, and this guy will be partial derivative of v with respect to x. So this thing will be u of x xy plus iv xy. So as a consequence of this definition over here is that the partial derivatives of u and v have to exist, at least with respect to x. Cool. Now we're going to do the same thing, but now we're not going to go towards 0 along the real numbers. We'll go along the imaginary axis, so go IB. So, oh, this is not equivalent, there's a one-way implication. Oh, I'm sorry, this is equivalent. This isn't equivalent to this, this is just, this implication is this way alone, right? So maybe I'm going to write this as, say, star star, definition of differentiability, and star star implies that we're going to do the same game, except now we go down with respect to beta. So it's going to be exactly the same as this thing right here. So let's just write directly from this. So we have the limit as I beta goes to 0, right? And then what we have, we're going to have u of x, y plus beta, plus iv, x, y plus beta, yeah? And then minus u of xy plus iv, xy, like this over IP, yeah? And then same thing, we break it up like this. And then what are we going to have? We'll have, okay, let's just write it out. So we have the limit as IP goes to 0 of u of x, y plus b minus u of x, y over IP plus I times v of x, y plus b minus v of xy over I times b. Yeah? Cool. And then what happens to this? This thing, so note that 1 over I is the same as I over I times 1 over I, which is just minus I, right? Because I times I is minus 1. So this thing over here will now become minus I, and again we can break up this limit of the sum into the sum of the limits, because both of these sums have to, both of these limits have to exist. So then this will be minus I, and now it's the partial of this, right? And then this guy here is just the partial like this. Okay. And this thing, yeah, is also equal to the derivative definition. So it's equal to the same complex number as this thing, yeah? So putting these things together, we get the so-called Cauchy Riemann equations, right? So from this and from this, we have that this complex number equals this complex number. This complex number is the same as this complex number, just from the definition of differentiability. So let's write that. That means that the real parts agree. So this is the real part and this is the real part. So this is true. And the imaginary parts agree. So this is equal to this. So I can write it as u of y is minus v of x. Cauchy Riemann equations. Okay, cool. So this has enormous implications. This says an awful lot. And I'm going to erase the board and we'll talk about what this says in a second. Do the following thing. So given f from omega into the complex numbers, okay, we've just learned what differentiability means. Yeah? So we say something is holomorphic at some z0 if it's differentiable there. So f is holomorphic if at z0 if f prime of z0 exists, and holomorphic on omega if f prime of z exists for all z belonging to omega. Okay, that is standard definition. We also use the words complex differentiable. Sometimes you see the words regular used, but that's a bit more old-fashioned. But this is the most standard definition. So it's holomorphic on a set omega if this exists, and typically we'll have omega be open because we need to have a bit of space to move in order to define this notion of differentiability, and omega is open. Okay. All right, cool. And what have we just learned? We've just learned that if it's differentiable, complex differentiable, at some particular point, then it satisfies the Cauchy Riemann equation. So to illustrate the meaning of that, let's do the following thing. So let omega tilde be the set of points in the plane which we get from our set omega. So if we draw omega tilde, it looks exactly like omega, except we're drawing it in the plane instead of in the complex plane, which might seem like an important distinction, but it's actually quite important, as we'll see in a second. Okay, and then f tilde from omega tilde into R2 by f of xy is equal to u of xy v of xy. Yeah, so now we get a function from this region in R2, we get from omega into R2, so omega tilde into R2, yeah, in this way. Yeah? And let's talk about what the derivative of this thing is, right? So hopefully you've all studied multivariable calculus. You're comfortable with what the derivative is. The derivative is 2 by 2 matrix, right? And it's given by this. So the first column is what happens when we take the partials with respect to the x, right? So it's u of x, xy, v of x, xy. And the second column is when we take the partials with respect to the y. So it's u of y, xy, v of y, xy. Yeah? Cool. So this guy right here is the general partial derivative for a function from R2 to, start again, it's the general derivative for a function from R2 to R2, but we also know that we have the Cauchy Riemann equations. Let's put them over here. We have that u of x is equal to v of y, and u of y equals minus v of x. So we can rewrite this thing like this. We're going to have u of xy. Right? What will this guy be using this thing? This will be minus. And this guy using this thing will be this. Right? In other words, this is going to belong to the space of conformal matrices. No? Okay, and conformal matrices, as we already discussed, or I already said at least, that are just some lambda times a rotation. So if we have any a minus b, b, a, then this is just lambda times, say, cosine of theta minus sine of theta, sine of theta, cosine of theta, where lambda is just square root of a squared plus b squared, and theta is arctan of b minus b over a. Okay, so these are very special matrices with very special properties, right? They are just rotations times a dilation. It's going to stretch or shrink and then rotate the plane. That's all these guys do, right? So what we find out is that this representation of a holomorphic mapping as a mapping from R2 to R2 actually satisfies a differential inclusion, right? So f tilde satisfies the differential inclusion D of F tilde belongs to the two-dimensional conformal matrices. Yeah? Cool. So, that has a lot of meaning. That has a lot of consequences for what F tilde can possibly be, because what is the point of differentiability? Differentiability tells us about the local structure of the function, right? So we learned this in Calculus 1. We take the tangent line. It looks incredibly close to the function. Therefore, we can do things like calculate the square root of 101 by using the tangent line, which we call a linear approximation in this context, right? So that is one of the key ideas of calculus, is to replace something complicated by something much simpler via differentiability. Yeah? In the context of functions from R2 to R2, how does this work? Well, what we have is that if F tilde is differentiable at, say, x0, y0, then what does it mean? It means that if we have some xy near x0, y0, then this thing is equal to the gradient, oops, I'm doing F tilde all the time, which is this 2 by 2 matrix, at the point this thing, acting on this vector, x minus x0, y minus y0, plus some little error. So the error is of order, let's write x minus x0. Let's write it like this. X minus x0, y minus y0, like this. So the error is acting on small vectors where error of w or mod w goes to 0 as w goes to 0. Right? This is the definition of differentiability. Yeah. So we can rewrite this as F tilde xy is this, which gives us this right here, plus order of x minus y0, y0. Yeah, so, and this thing right here is the tangent line, except now the tangent line is an affine mapping from R2 to R2, right? And this part right here is the linear part, so the F tilde of x0, y0 acting on xy. This is the linear part, and the affine part is this vector minus this vector. Yeah? Completely analogous to the tangent line in calculus, right? So if we do the tangent line in calculus, we have t of x is f prime of x, x minus a, plus f of a, right? Which is exactly this thing right here, where the f prime is this is this, and this is this. Yeah? Cool. So, what does that mean? That means that on a small scale, we have this error, which is a lot smaller than the scale that we're working at, right? We have this error, and then apart from this error, we just have a linear map, which is defined by this gradient here, yeah, which itself is a conformal matrix, which is a rotation times a dilation, plus this constant here. Yeah? So what's the consequences of that? The consequences of that are kind of huge. It means that the geometric information or the consequences of that are that on a small scale, the geometric action of our mapping is incredibly restricted. It's incredibly regular. And I'm going to have to erase some space to show you that. Okay, what have we learned? We've learned that when f is complex differentiable on omega, okay, and we write the representation f tilde satisfies this differential inclusion. Okay, and then from calculus, what we know, that means that f of x y minus, or f tilde of x y is okay, plus some small error. Okay, and this guy belongs to the conformal matrices, right? So let's draw a region, okay? Let's take some point where it's differentiable, say this is our x0, y0. And let's consider what the mapping, so it maps it to something like this, and let's say the image ends up here, x0, y0. And let's draw a little triangle around this guy. Let's draw not a good triangle. A little triangle around this guy, like this. Yeah, so if we take our points x, y around the outside of this triangle, like this, yeah, and then we see what happens under the action of f tilde, right? F tilde is mapping things across like this, yeah? Well, what's happening is that the difference between f of x, y and this thing, which is this point over here, which we think of as fixed because we're moving the x and y around, and this guy is just the point we've chosen, so it's fixed. So the difference between these two guys is given by basically this thing, right? And forget about this because it's very small compared to the scale of the triangle, right? Yeah. So as we move this thing along, right, we basically have this thing going on, right? So as we take our little vector here, from here to here, right, it's being acted on by this thing. Yeah? And if you think about what that actually means, it means that as we're moving along this line, then the image of it, at least from this part, will be a line, and there'll be some tiny error given by this. Yeah? Yeah, because if we move along this thing here, it's just an affine mapping, put it directly into this thing. This is a linear mapping, so we're just going to get an affine mapping out. So as we move along the line, we're just going to get a line. Yeah? So we move along the boundary of this triangle, we're going to have some kind of a triangle, like this. But even more, we have a triangle that's going to preserve the interior angles, right? Because over here, right, this is still behaving like this thing, right? Its behavior is being governed by this thing. And this thing is just a rotation times a dilation. So what will happen to this triangle is that it might be stretched, it might be shrunk, it might be rotated around, right? So it doesn't have to look like this, which is a bit too similar than the first one. It could be sent to some sort of triangle like this. Like this, say. Yeah? Or to some really tiny triangle like this. But the interior angles will remain the same because we are acting on it with a conformal matrix, which is just rotation times a dilation. Yeah? And the error that we have will just be from this thing, so it won't quite be a triangle, there'll be some wiggle around these lines, but as we get smaller and smaller, they're less and less noticeable. Right? That's exactly what this thing says. Yeah? So, even more, if we took not a triangle, if we took a smiley face around this point, so let's put a smiley face. This is the point over here. Let's put a smiley face around it like this. Then what will happen to this smiley face? It will be either shrunk or stretched. So this is the point f of x0. Oops, f tilde x0, y0. So the smiley face could be well, that's probably way too big. It could be expanded, or it could be shrunk, or it could be turned around, yeah? But it isn't gonna not look like a smiley face, right? Because on a very small scale, this thing right here is just an affine mapping, and we have a tiny error, yeah? So whatever we see happening over here, whatever we draw over here, will just be copied over here, rotated, and then stretched or shrunk. Better illustration, perhaps, is the following. Let us imagine that we are deforming a rubber sheet. So we have a rubber sheet, and it has grid lines on it. It has grid lines on it, so let's take some grid lines. Let's put some grid lines on this. So like a nice square structure like this. Then what's going to happen around the point here when it's differentiable? Well, these grid lines will be sent to some grid lines like this, and they might be expanded, or they might be shrunk. But they will, on a small scale, remain looking like grid lines. And this is f tilde of x0, y0. Yeah? Only on a small scale, right? You have to go on a very small scale to see this. Yeah? Cool. All right, so this is a very special property. This is extremely strange property to have. So on a bigger scale, we have our grid lines, and we can stretch and deform this sheet around the place, and it, we get all kinds of weird things looking or coming out from that. But as we look at a smaller and smaller scales, if we make a finer grid lines on the rubber sheet, as we look finer, then this structure reappears and looks like a grid configuration. That is what will happen as a result of this being true, which is just complex differentiability. And this is a really weird thing, right? Because if I asked you to create a function which has this property, that on a very small scale, these grid lines are sent to grid lines, in particular, the crossing of these grid lines retains its angle. So it crosses at 90 degrees on the image of these grid lines, right? That would be quite hard to do. It would be quite hard for you to come up with a function from R2 to R2 that actually does that. Probably the only thing you would come up with is just an affine mapping where it's just a constant plus a conformal linear mapping, right? Just a conformal matrix. Yeah? And you'd be right. Having difficulty coming up with such an example, it isn't so easy to think of things like this. except that we've just learned that there are many things like this. Any function that is complex differentiable has this property. Yeah? And there's a whole subject. We're going to learn this whole subject about this class of functions that are complex differentiable that have this property. Obviously, there's a wide enough family of such functions to make the whole subject worth studying, and that's one of the important parts of mathematics. So yeah, obviously there are lots of examples, and a surprising number of examples, and surprisingly ubiquitous occurrence of these things in other areas of math. You know? So there are indeed many functions that have this property, but it's a very strange and a very specific property to have. So this is the point where the calculus of functions from the complex numbers to the complex numbers completely bifurcates from the calculus from the real numbers to the real numbers, because having a function which is one-time real differentiable isn't nearly as restrictive as having a function that is one-time complex differentiable. There are a much wider variety of possibilities that functions that are one-time differentiable can have than functions that are one-time complex differentiable at every point in the domain. This is an extremely special property. And we are going to prove many spectacular theorems about functions that are one-time complex differentiable and those holomorphic functions because of this stuff. This stuff alone is already putting us in the realm of functions that are extremely nice in many, many ways. So this is where the real subject begins. This is where things get very different. And just to illustrate that just a little bit, let me talk about Wheels theorem. So as we just discussed, having a function which is holomorphic is equivalent to its realization as a function from R2 to R2 being inside the conformal matrices, right? So a natural thing to think of, if you want to try and generalize this theory to higher dimensions, is to ask yourself, well, what is the theory of functions that satisfy this differential inclusion in higher dimensions? And Liouville in 1851 did think about that. And he proved this in 3 dimensions, I think for functions with C3 regularity. It's true in all dimensions n bigger than or equal to 3. And the optimal regularity is not completely understood for when this theorem is true. It's completely understood for even dimensions, but not for odd. And that's an interesting open research question. But nevertheless, this is almost completely understood. And I'm just going to state this for smooth functions in Rn, and this is the generalization of Liouville's theorem. So suppose we have f from omega in Rn into Rn, which satisfies this differential inclusion, which is equivalent to the Cauchy Riemann equation that satisfies df belongs to this conformal matrices in Rn. So that's just lambda times rotations. And lambda's some real number, positive real number, and R is some two-dimensional rotation. Okay, then either f is affine, so it's just some constant vector in Rn plus a linear mapping whose gradient is inside the conformal matrices, or it's it's what we call a Mobius mapping in higher dimensions, and I have to build that up. All right, so what do we mean by that? So first, notice the following. So if we take x belonging to Rn, and we send it to x over absolute value of x squared, what does it do? That thing is inverting through the boundary of the sphere. So on the boundary of the sphere of radius 1, then it doesn't do anything, right? But if we are, we're going to see this guy in complex analysis too, if we are close to the origin, then we get sent down on a ray out towards infinity, right? And if we think about what this does, this is actually inverting through the boundary of the sphere. If we put a little smiley face over here, and then we map it with this mapping, then the smiley face gets mirror image flipped like this. Yeah? And the closer we are to the origin, the bigger it gets and the farther out it gets. That's what this thing does. And it's a non-trivial fact, but it is a fact that this thing preserves angles. This thing preserves angles. Yeah? Yeah? But it also inverts orientation. So the determinant of this thing is -1. And that's not what we want. In the conformal matrices, we want the determinant to be positive. So the determinant is -1. Well, let me not say it that way. Just let me say that if we take the derivative of this thing, then the determinant will be negative at any point. Okay. So this is not exactly what we want. So we need to reflect this again to get something which has the correct orientation. So any reflection will do. So if we take the mapping x goes to, say, -1, 1, 1, 1, all of these things are zeros, times x1, x2, blah, 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 xn, right? So that's just going to send us to -x1, x2, da, 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 xn. This is just reflecting through the first coordinate. Yeah, that's just an ordinary reflection through the plane defined by x1, right? So this thing is also a reflection. So let's call this mapping, say, let's call it A. Yeah? So this mapping is A. And let's call this mapping M. Okay. Then if we compose these two guys, then this too will preserve angles, because this one preserves angles, and this one too preserves angles. Yeah? Okay. So that will be an angle-preserving mapping. Yeah? And that is almost the definition of a Mobius transform in high dimensions, except that we don't have to care about inverting through the sphere centered on 0. There's no difference in doing this around the sphere centered on A. Right? Because 0 is nothing special for this purpose. So we could do this, and now, since this depends on A, let's call this M of A. So inversion through the sphere, radius 1, centered on A. Yeah? Then, we are almost there, except that to get an even more general expression, we could compose these things with some B, which is inside the conformal matrices. Okay, so then if we have X, we'll go to B composed with A, composed with M to the A of X. What will that do? It will invert through some sphere. It will reflect to have the positive orientation again, and then we will just rotate and dilate it once again with B. Yeah? That thing is the most this is the this is the one and only other this is the only non-trivial differential inclusion into this set. So we either have the affine one, which I claim is trivial, which I'll say is trivial, or we have this guy, and that's the only thing it can be. So all F is equal to B composed with A composed with MA in this sense here. And this A and this B is kind of non-important stuff. These are just linear mappings. The real heart of this guy is this thing, inversion to the sphere. So the reason this thing is not linear is because of this inversion to the sphere. So basically it's an inversion to the sphere, reflected one time, have positive orientation, and then just rotate and dilate it anywhere you want, which doesn't change anything much, right? So the real action is just the inversion to the sphere. So that is the one non-trivial mapping that satisfies this differential inclusion. So the theory of mappings that satisfy this differential inclusion is very limited, or perhaps the jury is strong, because there's only 2 examples, or morally speaking, only 2 examples. And so you could prove many spectacular theorems, but you're actually just proving it for this guy. So there's no higher dimensional complex analysis in that sense, which further highlights how very special, how very unique this object is. It only exists in 2 dimensions, and it's kind of remarkable that it exists at all. All right, good. So that'll be it for today. We will talk more about this next Tuesday. Have a good day.